Monotonicity and the first derivative test. The first derivative test for critical points. Assume that f of x is differentiable and let c be a critical point of f of x. So I want to stop right there for a second. The first derivative test is all about what is happening at critical points. So at a critical point, we may have a local maximum, we may have a local minimum, or we could have neither a local max or a local min. So if you remember, a critical point is where the derivative is 0 or undefined. So this test is going to be about figuring out which one of those is the case. Is there a y value at c that is a local maximum or a local minimum, or neither? The first derivative test says that if f prime changes from positive to negative at c, so if the derivative changes from positive to negative at c, then f of c is a local maximum. If f prime of x changes from negative to positive at x equals c, then f of c is a local minimum. So let's see what this translates to so that we can understand it just a little bit better. This really says if f of x changes from increasing to decreasing. So let's compare it. If f prime changes from positive to negative, well, if f prime is positive, f is increasing. And then if f prime changes to negative, well, then f changes to decreasing. So if a function changes from increasing to decreasing at some point c, at that critical point c, then f of c is a local max. So a change from increasing to decreasing, notice there would be a maximum occurring there. And the second one says that if f changes from decreasing to increasing, so if the derivative changes from negative to positive, so the original function changes from decreasing to increasing, then at f of c, there is a local minimum. So a minimum would occur in a change from decreasing to increasing. So it should be a very intuitive test if you understand the relationship between a derivative and the original function being increasing or decreasing. Alright, so here's a methodical process to using the first derivative test to analyze what's happening at critical points analytically given f of x. So what we want to start out by doing is first finding the critical points, and then plot the critical points on a number line to break it up into x intervals, and then determine the monotonicity of each interval. So determine whether each interval is increasing or decreasing. And if there is a change in monotonicity from increasing on some interval from a to c to decreasing on the interval from c to b, well, then there must be a local max at f of c. And if there's a change in monotonicity from decreasing on a to c to increasing on c to b, then there's a local minimum at f of c. And the last thing to note is that pay close attention to whether the question says to find the x value of the local min or max. Then the answer would only be the c value. But if it says to find the local min or local max, we have to substitute the critical point into f of x to find that y value, f of c. So it's the difference between, is the x value the answer, or do you have to plug x into the original function to find the y value that is the answer? Alright, so our first example, find the critical points of x cubed minus 27x minus 20 and determine if each is a local max, local min, or neither. So first find the critical points. So find where the derivative is 0 or undefined. So 3x squared minus 27, I want to set that equal to 0. So I'll go ahead and add 27 to the other side. Divide both sides by 3. I get x squared equals 9, so x equals plus or minus 3. So positive 3 and negative 3 are my critical points. And I want to decide what's happening at each critical point. Is there a local max there, a local min there, or neither? So what we do is we create our number line, and we mark the critical values, so critical points, negative 3 and 3, and then negative infinity and infinity. So our intervals go from negative infinity to negative 3 to 3, and 3 to infinity. So we break the number line up into intervals, and what we're really searching for is whether the derivative on these intervals is positive or negative. So remember, this is an interval, for f prime of x, the derivative. And here are intervals over the derivative where the derivative may be positive or negative. So we need to pick our test point. We need to find the sign of f prime, and that will tell us whether f is increasing or decreasing on that interval. So my test points will be -4, 0, and 4. So those are the easiest ones I think to choose, although you can pick any number in each of these intervals. And now we want to decide whether f prime is positive or negative at each of these test values. So f prime of x is this function here. So if I substitute in -4, well, -4 squared is going to be 16. 16 times 3 is going to be 48, and 48 minus 27 is positive, right? We don't have to care exactly what number it is, we just have to care if it's positive or negative. If I substitute in 0, this left side will be 0, so I'll be left with -27, or a negative value. And then substituting in 4, well, that's the same as substituting in -4 since we're squaring it anyway, so we're going to get out another positive. So, in other words, f changes from increasing to decreasing to increasing again. So we found the monotonicity over these different intervals on the original function f. Now we want to use this information to conclude what's going on at each of the critical points. So let me highlight the critical points for a second. The critical point is -3, so that's happening here, and +3, that's happening right here. So in this change from increasing on this portion of the graph to decreasing on this middle portion of the graph, well, change from increasing to decreasing would give me a local maximum. So a local max is going to occur then at the x value -3, at the critical point -3. And a change from decreasing to increasing over these two intervals that are next to each other is going to create a local minimum. So that local minimum must occur at this critical point 3. So the problem says find the critical points and determine if each is a local max, local min, or neither. So here's what our summary needs to look like. Since f prime changes from positive to negative at x equals -3, f changes from increasing to decreasing at x equals -3. So, by the first derivative test, f of -3 is a local max. So I need all of this justification to show that I truly understand the first derivative test and the results that I found using the sign chart. So in the past, on the AP exam, just drawing this sign chart was enough justification. Now they want sentence explanations because they were finding that students really just memorized what to do in the chart and didn't actually understand what was happening and how they satisfied the statement of the first derivative test. So the reason why it's working is because, well, if f prime changes from positive to negative, then f changes from increasing to decreasing. So by the first derivative test, at that changing value, f of -3, the y value, is a local max. So I'd have to say all of that same stuff about what's going on at 3. So by the magic of video lessons, here is the same statement, except now f prime is going from negative to positive at 3. So f changes from decreasing to increasing at 3, meaning the f dt concludes f of 3 is instead a local minimum. Alright, next example, analyze the critical points of this cubic function. So in other words, at each critical point, is there a local maximum, local minimum, or neither? So I have to find the critical points by finding the derivative. So that's going to be x squared minus 2x plus 1. And I'm going to have to set this equal to 0. So this is going to factor for me to x minus 1 equals 0. So my one critical point is x equals 1. So now I have to create my sign chart. and I'm going to go ahead and draw my number line. I'm going to plot 1. So my two intervals are only from negative infinity to 1 and 1 to infinity. So I'm going to go ahead and pick a test point in this interval. So I'm going to pick 0 in the first one and 2 in the second one. I want the sign of f prime, and that will tell me whether f is increasing or decreasing. So if I substitute in 0, I'm going to think about plugging it into this right here, x minus 1, x minus 1. So if I plug in a 0, I'll get a negative times a negative, so I will get a positive. And if I plug in 2, I'll get 1 times 1, which is a positive. Or we could have rewritten this as x minus 1 quantity squared and got the same result. So in other words, f is increasing on the first interval, and f is increasing on the second interval. So at my critical point that we found, x equals 1, well, this graph is increasing and then it stays increasing. So there is no local max or local min occurring at the critical point of 1. So at that location where I changed from interval to interval at that x value 1, if there's no change in monotonicity from either increasing to decreasing or decreasing to increasing, if it stays the same monotonicity, then there is no local max or local min. So at x equals 1, there is no change in monotonicity. So there is no local max or local min at f of 1. So since this is a cubic function, it's probably going to resemble something like x cubed, where there, has to be a little flatter, but where there was a place where there was a horizontal tangent line, but no local max or local min there. And now for a trig example, so we want to analyze the critical points of cosine squared x plus sine x on the interval from 0 to pi. So we need to find those critical points, we need to find the derivative. So this is the chain rule because this is cosine x as a quantity squared. So it's 2 cosine x, bring the 2 to the front, leave the inside the same, multiply by the derivative of cosine, which is negative sine, and the derivative of sine is cosine. So I'll go ahead and simplify this. This is negative 2 cosine x sine x plus cosine x. So now I want to set this equal to 0. So to do that, I'm going to go ahead and factor out what I have in common. I'm going to factor out this cosine x I have. So what I'm left with is negative 2 sine x plus 1. And now I have this product that I have equal to 0. So by the 0 product property, I can set each one equal to 0. So when does cosine x equal 0? And when does 2 sine x plus 1 equal 0? On the interval from 0 to pi. So cosine equals 0. So remember that cosine is the x value. So cosine equals 0 at pi over 2. So at x equals pi over 2. And that's it as far as the interval from 0 to pi goes. So only at pi over 2 does cosine equal 0. So now I need to solve for when does this equal 0. So I'm going to subtract the 1. So negative 2 sine x equals negative 1. Divide by negative 2. So when does sine x equal positive 1/2? So this is in quadrants 1 and 2. So 0 to pi is in quadrants 1 and 2. So all students take calculus. So all trig functions are positive in quadrant 1. Sine is positive in quadrant 2. So the two places where sine x equals 1/2, the two x values, are going to be pi over 6, and the angle in quadrant 2 with a reference angle pi over 6, so that being 5 pi over 6. So x equals pi over 6 and 5 pi over 6. So now, instead of breaking up the entire number line, I only have to break up the interval from 0 to pi, that's all I care about for this function, using these three values, these critical points. So my intervals go from 0 to pi over 6, pi over 6 to pi over 2, pi over 2 to 5 pi over 6, and 5 pi over 6 to pi. And we have to know our limitations. So if we try to pick a value between 0 and pi over 6, there's not a nice one on the unit circle that we can evaluate this derivative on. So this is going to be a graphing calculator problem. And it turns out that some nice test points to pick out are 1/2. So pi is 3.14. So 3.14 over 6, it's a little bit bigger than a half. So 1/2 is a nice number to use here, 1 here, 2 and 3 in each of my intervals. So I would have to then plug these numbers into my derivative function, into f prime of x on my calculator. So I would store this function in my calculator and evaluate these values to determine the sign of f prime of x, the sign of the derivative. And it turns out that when you do that, you're going to get alternating signs, so positive, negative, which means that in terms of f being decreasing or increasing on this first interval, we are increasing, then decreasing, then increasing, and then decreasing. So we have a graph that's changing from increasing to decreasing at pi over 6. So there is a local max at f of pi over 6. And then we have a graph that's changing from decreasing to increasing. So we have a local min at f of pi over 2, and then finally we're changing from increasing to decreasing, so we again have another local max at f of 5 pi over 6. So I'm going to skip writing out the conclusion, but we would have to again justify, since f prime changes from positive to negative at pi over 6, then f changes from increasing to decreasing at pi over 6, so there is a local max by the FDT at f of pi over 6, etc. for each and every one. So some of these problems are a little bit more complicated and require the use of a graphing calculator, but finding the critical points is not a graphing calculator problem. So you would have to be able to solve trig equations such as these in the general course of problems without using a graphing calculator. Alright, in this example, analyze the critical points of f of x equals ln x minus x on 0 to infinity. So first we need to find the critical points, so set the derivative equal to 0 and find where it's undefined. So the derivative of ln x is 1 over x minus 1. I'm going to need to find common denominators to turn this into one rational function, so it's going to turn into 1 minus x over x. So I turned 1 into x over x and then combined the two fractions with common denominators. So my critical points are going to occur where 1 minus x equals 0 and where the denominator equals 0. So in other words, this is at x equals 1 and x equals 0. Well, I was told to analyze the critical points on open 0 to infinity, so that means that this is a value I ignore. Not to mention 0 cannot be substituted into the natural log function anyway. So my one and only critical point is at x equals 1. So now here's where I create my intervals. So 1 is on my number line, and I have to start my number line at 0 and go up to infinity. So if we don't need to draw the number line, we can just jump straight to creating the intervals 1 to infinity. It's just to help guide us to go from left to right, put smaller numbers on the left and biggest numbers on the right. And then we pick our test point. So unfortunately this one would have to be a fraction, and this one we could choose the whole number 2. And remember that we're substituting the test points into the derivative, so we're interested in the sign of f prime of x. So if you were thinking, well, I don't know what natural log of 1/2 is, it doesn't matter, we're plugging 1/2 into the derivative function. So if I plug 1/2 into the numerator, 1 minus 1/2, that's positive. 1/2 is positive on the bottom, so I get a positive value. But if I substitute in 2, the top would be negative and the bottom is positive, so I would get a sign change from positive to negative. So f, we have to decide whether f is increasing or decreasing. So we have increasing where the derivative is positive and decreasing where the derivative is negative. So a change from increasing to decreasing means local max. So we will summarize this last one as, since f prime changes from positive to negative at x equals 1, f changes from increasing to decreasing at x equals 1. So by f dt, f of 1 is a local max. The last thing we're going to do is use the first derivative test to analyze critical points graphically given the first derivative. So to find critical points, we're going to need to find the x-intercepts on the graph of f prime of x, because that's where the derivative equals 0. And to find where the derivative is undefined, we're going to have to find non-asymptotic places of discontinuity on the graph of the derivative, so jumps or holes. So we don't want to find asymptotes because then those values are not in the domain of the original function, so they're not critical points. And then what we have to analyze is whether the graph of the derivative changes from positive to negative at those x values, those critical point x values, so changes from above to below the x-axis. If so, then there's a local maximum at f of c. But we cannot find f of c exactly because we're looking at the graph of the derivative. And if the derivative changes from negative to positive at x equals c, below to above the x-axis, then there's a local minimum at f of c. But again, we cannot find f of c if we don't have the original function. Alright, first example. Below is the graph of f prime of x. Find the critical points of f of x and determine if each is a local min, local max, or neither. Alright, so critical points occur where the derivative is 0 or undefined. So to find critical points, I'm looking for the x-intercepts, or jumps or holes. So there are no jumps or holes, just two x-intercepts at -1 and 3. So my critical points are -1 and +3. And now determine what happens at each one. Is it a local min, local max, or neither? So at x equals -1, let's think about what is happening to the derivative. The derivative at -1 is changing from left to right, from above the x-axis to below the x-axis. So as I move in this direction, the graph was above and changes to below. So at x equals 1, f prime changes from positive to negative, right? From above to below the x-axis. So if f prime changes from positive to negative, f changes from increasing to decreasing. So at x equals 1, f prime changes from positive to negative. So f changes from increasing to decreasing. Sorry, not degrees, decreasing. So by f dt, f of -1 is a local max. So we can't actually find f of -1 because this is the graph of f prime of x. So sometimes students want to say, oh, well, f of -1 is 0. That's not true. F prime of -1 is 0. I don't actually know what the graph of f of x looks like at all. Well, not at all, but just not enough information to specifically find f of -1. So now we have to analyze what's happening at x equals 3. So at x equals 3, let's go ahead and look at the graph of f prime of x. So at 3, as I move, again, from left to right, the derivative is at first below the x-axis until it reaches 3, where then it switches to above the x-axis just after 3. So f prime changes from, in this case, negative to positive. So f changes from decreasing to increasing. So by the first derivative test, f of 3 is a local min. So when we're looking at the graph of the derivative and we want to find critical points, we look for the zeros, or the x-intercepts. And then when we're looking for whether or not those critical points are local mins, local maxes, or neither, I need to look for a change from either positive to negative on the graph of the derivative or negative to positive on the graph of the derivative, and then apply the first derivative test rules. Alright, same type of problem. Here's the graph of f prime of x, find the critical points and what's happening at each critical point. So my critical points are going to be where the derivative is 0, or my x-intercepts, so -4, 0, and 2. So those are my critical points, -4, 0, and 2. And now we're going to figure out what's happening at each one. And I'm going to try to shorthand this as much as possible. So -4, let's think about what's happening on the graph. From left to right, near -4, on the left side of -4, I'm below the x-axis, so my derivative is negative, and as I move to the right, I switch to being above the x-axis, so my derivative changes to positive. So at x equals -4, f prime goes from negative to positive, so f changes from decreasing to increasing. So by the f dt, I know that f of -4 is a local minimum. So if I have a change from decreasing to increasing, there's a local min. Now let's analyze what's happening at the next critical point, 0. So near 0, as I move from left to right, I start out above the x-axis, so I start out with a positive derivative, and then I switch to being below the x-axis, so I change to a negative derivative. So near 0, f prime changes from positive to negative, which means f changes from increasing to decreasing. So by the first derivative test, f of 0 is a local max. And then we're finally going to analyze what's happening at +2. So at x equals +2, if we take a look at the function from left to right, we start out below the x-axis and then switch to above the x-axis as I move from left to right. So f prime changes from negative to positive. So f changes from decreasing to increasing. So by the first derivative test, f of 2 is another local min. So I have 2 local minimums and 1 local maximum. So I know that the critical points where they occur are at -4, 0, and 2. So this is kind of the most shorthand way to possibly fully answer the question and justify it using the first derivative test. Before I move on, the last thing I want to point out is these little pluses and minuses. So if you've previously used a little plus or minus to indicate whether the slope of the tangent line is positive or negative, that's not what I'm doing here. What I'm doing is saying that plus means that the graph is above the x-axis and minus means the graph is below the x-axis. So please don't confuse the plus and minus to correspond to the slope of the tangent line, because this is the derivative graph. I'm reading whether it's above the x-axis or below the x-axis. That is what the plus or minus signs are referring to. Alright, so we have another example. Here's another graph of the derivative, and same instructions: find critical points and determine what happens at each. But there's going to be a slightly different result on one of these critical points. So I have a critical point at -2, at 1, and at 3 on the x-intercept values of the derivative. So those are my 3 critical points. So now let's try to decide what's happening at each. So what's happening at -2, at 1, and at 3. So -2 is where something slightly different than any of the other examples happens, is that as I move from left to right, as I start from the left side of -2, I have a positive derivative. I have a derivative that's above the x-axis, and then I have a derivative that's above the x-axis over here. So my derivative stays positive. So f prime goes from positive to positive, so there is no sign change. So what that means is that f of -2 is neither a local min or local max. Because you'll notice on the graph of the derivative, there's a bounce off of the x-intercept. So even though I have an x-intercept, there is no sign change on the derivative, so that means that the original function can't change its monotonicity. But at x equals 1, we are going to have a change from above the x-axis to below the x-axis. So I am positive and then negative. So if f prime goes from positive to negative, f goes from increasing to decreasing. So that must mean that at f of 1, by the f dt, I have a local max. And then analyzing the last critical point, 3, from left to right, I go from below the x-axis to above the x-axis, so f prime goes from negative to positive. So f goes from decreasing to increasing, so that means that f of 3, by the first derivative test, must be a local minimum. Alright, so this is the last example, and it's a very different example. So I am still given the graph of the derivative function, and I need to find the critical points and whether the critical point is a local min, local max, or neither. But this time I don't have any x-intercepts. I do, however, have places where the derivative is undefined, and that x value is 0. So my critical point is 0, based on this being my derivative function. So now I have to figure out, well, what's going on at x equals 0 as far as the sign of f prime of x. So on the left side of 0, as I move from left to right, so on the left side of 0, the derivative is below the x-axis, the derivative is negative, and then right after 0, the derivative starts being positive again. So f prime changes from negative to positive, and that change happens at 0, so f must change from decreasing to increasing. So we can still apply the fundamental or the first derivative test and say that by the f dt, f of 0 is a local minimum. And what I wanted to point out is this is a very unique derivative, and maybe you recognize it to be the derivative of the absolute value function. So if I were to graph the absolute value function, so there is one place where the derivative does not exist at 0 at this sharp turn, and notice it is a local minimum of the graph of the absolute value of x. And so we are able to find that by reading the graph of f prime of x and finding where the derivative does not exist to find the critical point, and then analyzing it in the same way using the first derivative test.